Hi, I'm Wanrong from Harvard University, and I'll be presenting our paper, Leakage of Dataset Properties in Multi-Party Machine Learning. This is joint work with Shruti Tople, she's at Microsoft Research, and Olga Ohrimenko, she's at the University of Melbourne. Modern machine learning models have been shown to memorize personal information about their training data. It raises privacy concerns regarding their use and release in practice. Specifically, what can we learn about the dataset D from a model F of D? Leakage of sensitive information about the data has been shown by membership inference attacks to infer whether or not a particular person in the dataset. And individual attribute attacks or model inversion attacks to infer one entry of a particular person. For example, whether a person admitted cheating on their significant other. The majority of the existing work study attacks that focus on leakage of information about individual record in the training data. However, in many settings, the global properties of a dataset may also be sensitive. The global property of a dataset are confidential when they are related to the proprietary information or intellectual property that the data contains. And its owner is not willing to share such information. For example, when hospitals release information about patient states, they might be concerned about whether the demographic information about the patients, like gender and race distribution, can be leaked. Or when insurance company providing quotes, they might be concerned about whether the income distribution of its customer be leaked. Some other proprietary information is also considered as confidential, such as the proportion of chemicals in a new drug and the most purchased product of the company. In this work, we depart from individual record leakage and focus on dataset level leakage. Specifically, we study what F of D reveal about the privacy attribute A. If you think dropping A is a potential solution, we will show that this is not sufficient. We'll also show the leakage of sensitive information is possible when A is even irrelevant to the final task. Our primary focus is on inference dataset level properties in a centralized multi-party machine learning setting. Secure multi-party machine learning allows several parties to jointly train a model on their combined data without explicitly sharing data with each other. For example, several hospitals send their data to a central server and jointly train a model using some mutually agreed upon code. Since multiple hospitals have different patient groups, they may have separate views of a drug test or treatment strategy. A model trained on combined data would be more useful for more broader patient groups. We know that a recent work also studied leakage of dataset level properties, but they focus on the single party setting, and they assume white box access to the model. Our threat model is they are all honest parties with one honest but curious party. And this is a realistic setting since a malicious party will not alter its own data or change the machine learning code. Otherwise, they will exclude the malicious party in the training process. And the attacker only has black box access to the final model. And they want to say if it's possible to infer the global properties about other parties' sensitive attributes. We perform an attack to estimate the proportion of the sensitive attribute. Our attack is based on shadow model training technique as previous work. It requires only black box access to the model and can extract the distribution of a sensitive attribute with small number of inference queries. Here's our attack model pipeline. In the shadow model training stage, half of the shadow model are trained with the property P, then the attacker is trying to learn, and then half without it. And the sensitive attribute properties is modeled by the distribution of a particular attribute property P. For example, the majority of the samples are females or males. Then in the meta-model training stage, each shadow model is queried on a dataset, D attack. And I'd like to highlight that our attack vector is different from previous work. to infer global properties about training data. The attacker needs to combine information from multiple inferences made by the model. So the attacker measures how the model performs on a sequence of key records, which is the opposite to a single record used in the previous work on individual attribute and membership inferences. And then the meta classifier can be any classification models. Here's the execution of the attack on the target model. Once we get the target model from the training process, the target model is queried on the D attack, which is the same attack dataset as we used in the attack pipeline. We also concatenate the probability prediction vectors as an attack vector, and to fit the trained meta classifier, and then get the final prediction of the property P. For the experimental setup, we consider several datasets with tabular data, graph data, and text data. And 4 kinds of multi-class classification models includes multi-layer perception, logistic regression, and LSTM for language model, and GCN for graph model. Our primary focus is the multi-party setting. We also study the single-party setting where only one party released a machine learning model. And the goal is to infer the property of the training dataset, given only the black box access to the machine learning model. Additionally, we give a fine-grained attack technique for model updating setting, where a new party is drawn in over time, and we want to infer the property of the new party's dataset. And the fine-grained attack technique can also be used for distinguish more precise distribution of the benign party's dataset, beyond only inferring the majority. Here we will show the main result, with a focus on 2 parties and binary attribute properties. We evaluate the attack accuracy when the sensitive attribute A is used for training or not, with several different attribute A set as the A. And this is a histogram of the attack accuracy. The baseline is random guess, which is 50%. The blue bar is training with A, and the orange bar is dropping A during the training. Although removing the sensitive attribute column during training process sounds like a solution, from our results, we can see even when we exclude A, it's still better than random guess. And it's very close to when A is included. So the information is leaked regardless of whether the training dataset contains a sensitive attribute or not. To understand how the correlation between A and other features influence the attack, we also identify the correlations present in the dataset. And the most interesting case is A is correlated with other features, but uncorrelated with the target variable Y. We determine the correlation by several correlation factors. For example, for the adult datasets, the target variable is education level, and the primary base score between gender and the target variable education level is 0.217. From a histogram, we can see our attack can still achieve high accuracy for this case. And accuracy is higher than 0.7 for the 3 cases. And for the first example, it's still better than random guess. So our attacks show that the leakage of population-level property is possible, even in the case when the sensitive attribute is irrelevant to the task. As a conclusion, we show leakage of sensitive dataset properties is possible, even when the sensitive attribute column is dropped during training. And the sensitive attribute has low or no correlation with the final task. So our attack suggests that the sensitive attribute leakage is a significant privacy vulnerability. Unfortunately, the existing technique for secure computation and differential privacy are not directly applicable here, because our attack is oblivious to the exact techniques used for secure computation. And differential privacy only guarantees record-level privacy. Although group differential privacy can be applied here, but it comes with high cost in accuracy. We hope our results will motivate researchers to explore protection techniques for dataset-level property leakage. Here's our contact info. Please feel free to ask us questions if you have more concerns and questions regarding our paper. And thank you.